Last time, we learned that Newton's laws with mass lead to second-order ordinary differential equations that we convert into first-order ODEs with multiple equations. What if we want to go backwards from a first-order ODE with multiple equations to a second-order ODE, using the same example as before, where we have a wall, a spring, a damper, both of which are connected to a mass that might have an external force. We have equations of the form x dot equals v and v dot equals f of x v. The fact that x dot equals v implies that x double dot equals v dot. And we know what v dot is equal to. That's equal to f of x v. But we also know that v is equal to x dot, so we have f of x dot. That means if we take the time derivative of this top equation, we can conclude that x double dot is equal to f of x and x dot, which is the same second-order differential equation that we had before. This procedure of going back and forth between first-order and second-order ODEs is confusing primarily because it is so simple. It is just a relabeling trick that you have to get used to. As an example, consider y dot is equal to z, and z dot is equal to ay plus bz. The same trick that I just showed you tells you that y double dot is equal to z dot, and therefore y double dot is equal to ay plus by dot. Last time I talked about Newton's laws with mass, but what do we do if there are several masses? For instance, what if I take a slinky and I bind together pieces of the slinky in the middle so that they act like masses? If I then do this, the two masses act independently, and they probably have independent states. So if I diagram this system, and I draw a wall, this left wall represents one of my hands, and then I draw a spring. I'm going to label that x1. I draw a mass. I'm going to label that m2. I draw another spring that I'm going to label x3, and another mass that I'm going to label m4. Lastly, there's a spring labeled x5, and then at the right-hand side, there's another wall that represents my other hand. Newton's laws tell us that the sum of forces at each mass must be equal to the mass times the acceleration of each mass, where acceleration is defined to be positive if the mass is moving to the right, and the velocity of each mass is measured relative to the left wall. So the sum of forces acting on mass 2 must be equal to m2 times a2. The sum of forces acting on mass 4 must be equal to m4 times a4. Also note that the spring positions are not independent of each other. If the distance between the walls is L, then the sum of the spring positions needs to be equal to L. That is, x1 plus x2 plus x3 must be equal to L. Now I'm going to choose the states of my ODE to be x1, v2, x3, and v4. You could make other choices. Note that a2 is equal to v2 dot, a4 is equal to v4 dot, and x5 is equal to L minus x1 minus x3 because of the length constraint. Moreover, v4 is equal to x1 dot plus x3 dot. That implies that x3 dot is equal to v4 minus v2. Plugging in constitutive laws for Newton's equations gives us minus k1 x1 plus k3 x3 is equal to m2 a2. It also gives us minus k3 x3 plus k5 x5 is equal to m4 a4. And then this x5 is equal to L minus x1 minus x3. To make things simpler, let's set all of the spring constants to be the same k and set the mass is equal to 1. If we rearrange this, we can get a first-order linear constant coefficient differential equation with 4 equations, one for each state. We get x1 is equal to V2. We get V2 dot is equal to minus k x1 plus k times x3. Then we get x3 dot is equal to V4 minus V2. And lastly, we get V4 dot is equal to minus k x3 plus k times L minus x1 minus x3, where that last term is equal to x5. That is, we have an equation that is of the form d dt of something is equal to f of something, just like I mentioned in the first lecture on Newton's laws, but the something now has 4 variables instead of just 1. If we made a mistake and made a bad choice of state, we would not be able to get an ODE with these 4 variables as the state. As you might guess, if we had lots of masses, we would end up with lots of equations and lots of states, which might make keeping track of things a bit unmanageable. We are going to address this in lectures 11 and 12. Things to remember from today. Newton's laws will give you ODEs describing the time evolution of a system that has multiple masses, but the number of first-order equations you get will go up with the number of masses. Typically, you should expect to have 2 equations for every mass. Lastly, note that in the equation for the masses, the total distance between the walls, L, is playing the role of an external force in the equation. And this is quite common any time there is a constraint between variables, in this case x1, x3, and x5.